Imagine telling an AI, "Fix the bug in my project." A traditional chatbot might explain what the problem could be and give you some code to try, but modern coding agents can do something very different. They can open your repository, search through files, understand the project structure, read the relevant code, run commands, execute tests, modify files, inspect errors, and keep trying until the problem is solved. So what exactly makes a coding agent different from an ordinary AI chatbot? The answer is surprisingly important. It is not just the AI model. A coding agent is an entire system built around a language model. The model provides reasoning and code generation, but another layer of software gives that model access to the environment, tools, memory, context, permissions, and feedback. This surrounding system is often called an agent harness, and when it is designed specifically for programming, we can think of it as a coding harness. Understanding this architecture helps explain why tools such as Claude Code, Codex, and other modern coding agents can feel dramatically more capable than simply asking an AI to write code. Let's start with the most important distinction. An LLM is fundamentally a system that takes tokens as input and generates tokens as output. You give it a prompt, and it generates a response. An agent adds something much more powerful, a loop. Instead of simply going from prompt to answer, the system can observe its environment, decide what to do, perform an action, observe the result, and then decide what to do next. In simple terms, the loop is observe, think, act, observe again, and repeat. For coding, this changes everything. Suppose you tell an agent, "The authentication tests are failing, fix them." The agent doesn't immediately start writing random code. First, it might inspect the repository. Then it might search for authentication-related files. It might find the relevant tests, run them, and examine the error message. It can then inspect the implementation, make a change, run the tests again, discover another problem, make another change, and continue until the tests pass. This is fundamentally different from simply generating code from a prompt. The model is not working from imagination alone. It is interacting with a real software environment and receiving feedback from that environment. And this brings us to the first major component, repository context. A coding agent needs to understand what it is working on. If you say add authentication, that instruction is incomplete. Authentication in a React application using Firebase is very different from authentication in a Django application connected to Postgres. The agent therefore needs to discover the project structure, dependencies, configuration, documentation, tests, Git status, and sometimes project-specific instruction files. For example, a repository might contain an agents.md file that tells the agent which package manager to use, how tests should be executed, which directories are generated automatically, or which files should not be modified. This information gives the model a map of the environment before it starts making decisions. The second important component is prompt construction and context reuse. Coding agents can make many model calls during a single task. Imagine an agent working on a bug for 30 minutes. It might inspect dozens of files, execute many commands, run tests repeatedly, and make several attempts. If the entire repository information, tool definitions, and instructions are rebuilt from scratch for every model call, that becomes expensive and slow. A better system separates stable information from changing information. Stable information includes system instructions, tool definitions, and project rules. Changing information includes the latest test result, recent file changes, command output, and the current task state. The stable part can often be reused or cached, while the dynamic part changes as the agent works. This is important because agent performance is not just about how intelligent the model is. Efficiency also depends on how intelligently the surrounding system manages the model's context. Now we come to one of the most important parts of an agent, tools. A normal chatbot might tell you, "Run the test suite." A coding agent can actually run the test suite. The model might request an operation, such as reading a file, searching for a function, applying a patch, checking Git status, or executing a command. The harness receives that request, validates it, checks permissions, executes the operation, and returns the result to the model. So the model decides what it wants to do, while the harness controls how that action actually happens. This separation is extremely important. Imagine the model wants to execute a shell command. The harness can check whether the command is allowed. It can also restrict which directories the agent can access, whether it can make network requests, whether it can delete files, and whether a particular operation requires human approval. This creates a security boundary around the model. And as coding agents become more powerful, these boundaries become increasingly important. A language model generating text is one thing. A language model capable of modifying files, installing packages, accessing databases, running shell commands, and interacting with the operating system is something very different. That is why permissions, sandboxing, file system restrictions, command approval, and least privilege access are becoming fundamental parts of agent design. But tools create another challenge: context. Every time an agent reads a file or runs a command, the result potentially becomes part of the model's context. Imagine the agent reads 20 files, performs 50 searches, runs several builds, and receives thousands of lines of logs. If everything is kept forever in full detail, the context can become enormous, and more context does not necessarily mean better reasoning. In fact, too much irrelevant information can make an agent worse. The model may need only 3 things to solve the current problem: the relevant function, the associated test, and the latest error. But if its context also contains thousands of lines from unrelated files, old logs, previous failed attempts, and duplicate information, the important details become harder to identify. This is why context management is such an important part of a coding harness. Large outputs can be clipped. Repeated information can be removed. Old conversations can be summarized. Recent information can be kept in greater detail, while older information is compressed. Think of it as maintaining a working memory. Instead of remembering every single thing that happened with equal importance, the agent tries to preserve the information that matters for the current task. This leads naturally to another component: session memory. Long-running coding tasks cannot always be completed in one conversation. An agent may work on a project today and need to continue tomorrow. If everything is lost when the session ends, the agent has to rediscover the entire task. A better system stores persistent state. It can remember what the task was, which files were changed, what tests were failing, what approaches were already tried, and what remains to be done. There is an important distinction here between a full transcript and working memory. The transcript is the historical record of everything that happened. Working memory is the compact summary of what matters right now. For example, instead of carrying thousands of previous messages, the agent might maintain a concise state saying, "Authentication is being implemented, the OAuth callback is complete, the refresh token test is failing, and the next step is to inspect token expiration logic." That small piece of information can be much more useful than the entire history. Another powerful idea is delegation through subagents. Suppose the main coding agent is implementing an API, but needs to understand where a particular database model is defined. Instead of doing all the investigation itself, it could delegate that task to a smaller subagent. The subagent searches the repository, finds the model, examines related files, and returns a concise answer. The main agent can then continue its primary task. This creates a structure similar to a software engineering team. One agent might focus on implementation, another on testing, another on repository research, and another on documentation, but subagents also need boundaries. If agents can endlessly create more agents, or freely modify every part of the repository, the system can become chaotic. So subagents may have restricted tools, limited context, limited directories, limited execution time, or a maximum delegation depth. The goal is to give each subagent enough power to complete its specific task, but no more than necessary. Now we can put all of these pieces together. A modern coding agent starts with a user goal. The harness provides repository context, project instructions, tools, permissions, memory, and relevant history. The model receives carefully selected context and decides what to do. It might search the repository. The harness executes the search. The result goes back to the model. The model analyzes it and decides to read a file. The harness reads the file. The model decides to modify the code. The harness applies the change. Then the model runs tests. The tests fail. That failure becomes new information. The model analyzes the failure and tries again. This creates the core agent loop: observe, decide, act, and observe again. And this feedback loop is one of the biggest reasons coding agents can appear much more capable than ordinary chatbots. Imagine the difference between these two experiences. In the first, you ask an AI, "Fix this bug." It generates a possible solution. In the second, you tell an agent, "Fix this bug." The agent investigates the repository, finds the relevant code, runs the failing test, changes the implementation, runs the test again, discovers a regression, fixes it, runs the complete test suite, checks the git diff, and then reports what changed. The underlying model might be similar, but the surrounding system is completely different. This is why it is useful to think of the model and the harness as separate layers. The model provides intelligence. The agent loop provides iterative decision-making. The harness provides tools and control. Context management provides focus. Memory provides continuity. Permissions provide safety. And tests and other development tools provide external feedback. This also explains why context engineering is becoming just as important as prompt engineering. Early AI applications focused heavily on the question, what should we put in the prompt? Agentic systems require a broader question. What information should the model see right now? What actions should it be allowed to take? And what should happen after it takes an action? That is context engineering. It involves selecting relevant files, managing history, compressing old information, choosing useful tool outputs, maintaining working memory, and removing unnecessary information. And there is an important lesson here. A huge context window does not automatically solve the problem. The goal isn't to give the model everything. The goal is to give the model the right information at the right time. Finally, there is perhaps the most important component of all: verification. A normal code generation model can say, this should work. A coding agent can actually check. It can compile the project. It can run tests. It can execute a linter. It can inspect logs. It can check the Git diff. And if something fails, it can use that failure to guide its next decision. This turns coding from a one-shot prediction problem into an iterative feedback process. The agent doesn't have to be perfectly correct on its first attempt. It can make an informed attempt, observe what happened, and improve the result. That is a fundamental shift. And it points toward a much larger change in how we think about AI. The future of AI is not simply about models that generate better answers. It is increasingly about systems where models can interact with environments. A research agent can search, read, compare, and investigate. A data analysis agent can inspect data, write code, execute it, analyze the results, and revise its approach. A coding agent can inspect a repository, modify software, run tests, and verify the result. So the real evolution is from prompt and response toward goal. Planning, action, observation, feedback, memory, and continuation. The coding agent is one of the clearest examples of this transition. It shows us that a powerful AI model alone is not enough. The environment around that model matters enormously. The model is the reasoning engine. The harness is the system that allows that reasoning engine to actually work. And when you combine a capable model with good context, reliable tools, persistent memory, strong permissions, intelligent delegation, and continuous verification, you get something much more powerful than a chatbot. You get an AI system that can actually participate in the software development process. And that is what makes modern coding agents so interesting. They are not simply AI that writes code. They are AI systems designed to understand a software environment, take actions inside it, learn from the results, and keep working toward a goal.